Hi, everyone. My name is Paige Chesshire, and today I'm talking about a paper that is currently under review entitled Completeness Analysis for 3,158 United States Bee Species Identifies Persistent Data Gaps. This paper was written with all of the co-authors listed here. So we know that there are about 8 million bee specimens in United States collections, whether they're digitized or undigitized. But with the current rate of digitization, it could take decades to get all 8 million of these transcribed. However, numerous studies are already documenting bee declines. Oftentimes, this data is showing geographic and taxonomic biases and sampling biases. And so documenting all bee distributions is a fundamental step to combating the Wallacean shortfall. Completeness analyses can provide a very simple metric to quantify the Wallacean shortfall and see where we are having these biggest geographic and taxonomic gaps or biggest geographic hotspots. So the goals of this paper was to conduct data completeness analyses of bee assemblages at 4 spatial scales. Our finest resolution was 30 by 30 kilometers, and our coarsest was 220 by 220 kilometers. A second part of our paper was to see how might this percent data completeness improve if all 8 million specimens in the United States were digitized. So this estimate of 8 million came from a count done in 2019 by the iDigBees project that inventoried United States collections. And even though we know there are 8 million specimens roughly in these US collections, about 25% of them are already digitized, so roughly 2 million records are already digitized, and about 20 to 25% of the remaining specimens likely correspond to duplicate occurrences or to localities that are outside of the United States. So when all is said and done, there's about 4.7 million records, unique records, that could be digitized and added to data. And so we use this information to project 4.7 million records and add them to our data sets and rerun completeness analyses. We see that even with the addition of the projected data points, the same geographic and taxonomic hotspots as well as biases exist. And so the takeaway is that the complete digitization of all 8 million bee specimens in the United States collections will likely be inadequate. And so we should still keep digitizing, but simultaneously we must initiate new strategic surveys and we need to target the undersampled taxa or locations. There are 4 manuscripts in progress that are tangentially related to this paper. And then we also hope to provide projected assemblages to conservationists and regional research efforts. The methods for our completeness analyses involved a starting point of 2.8 million North American bee records. And then after cleaning the data, very extensive cleaning and dwindling it down to just the contiguous United States, we were left with about 1.923 million records for 3,158 bee species. This is nearly 88% of US bees. For every single bee species, we made a range map, and we used the minimum convex polygon method to create this range, which it uses the smallest polygon that can encompass the distribution of occurrence points for a species. We went a step forward and masked by suitable land cover type using landfire data. So instead of having just a big polygon, a single block that covers all pixels, we filtered out pixels that were determined to be unsuitable habitat for a certain species. We repeated this process for all species and then stacked them together such that 3,158 polygons later, we had this ensemble model of expected bee richness in the country. And so essentially we have a map of expected bee species richness at whatever resolution we chose. We repeated this process for observed richness, but instead of stacking range maps for each species, we stacked the maps of occurrence records for all the species. And then we were able to obtain observed richness values for every single pixel. And we could divide those values by expected richness values for the same pixels to get percent data completeness across the United States. And then we obtained an average percent data completeness for the United States. We did this for all bees as a group, as well as on a family level. And we did it at 4 spatial resolutions. Results indicate that using our currently digitized data at the finest resolution of 30 by 30 kilometers, the average percent data completeness is not even 6% complete. And there is a large amount of variance across pixels. We see this large variance across pixels regardless of spatial resolution. And at the 220 by 220 kilometers resolution, which is our coarsest, we still see that bee data is currently not even 40% complete. So a lot of this can be attributed to sampling biases. We're seeing geographic and taxonomic gaps in certain areas of the country. The meat of this project, though, was to project future completeness. And so we used the 2 million currently digitized records to create additional bee records. The process involved generating occurrence points for every bee species. And remember, these points represent already collected, just undigitized specimen records. For every species, the number of points generated was relative to its range size, and the new points created had to be placed within their predetermined range. We had 2 different projection methods, the constrained method and the random method. So for the constrained method, this is a modified version of the nearest neighbor method from Clark and Evans, 1954. Essentially, the new records were spatially constrained to maintain the clustered distributions that are seen for most species. And so this considers the fact that data distribution tends to be non-random, whether that is a result of true species distributions or whether it's a result of sampling biases. And also, this considers that there are often geographic biases in specimen-based data sets that can result in this same data clustering. So if you look at this map here on the left, we have a map and a range with currently existing points for a species, or currently digitized points, I should say. And then with this constrained method, the projected points had to fall within a certain distance of a pre-existing point. On the other hand, for the random method, the projected records still had to fall within that species' predetermined range, but there were no additional spatial constraints. So again, we have our currently digitized points within the range on the left map here. But then for the random method, the projected points could fall anywhere within the range. And we realize that this is unlikely and the undigitized data likely does not look like this, but it does provide the other end of the spectrum for our 2 analyses. Results from the constrained method show that even when we included projected records, we are seeing only about 12% completeness increases across the country. And these increases in completeness are occurring in the same places where they are already taxonomic or geographic hotspots. And we're actually seeing these 12% increases at all 4 spatial resolutions. On the other hand, the random method got us close to 100% completeness at all resolutions, whether we did it on a family level or for all bees as a group. And so the comparison of the 2 methods was telling. For the constrained method, we do see these more moderate completeness increases, but it underscores the fact that the use of records that are biased toward roads, field sites, municipalities, universities, aka clustered data, can majorly constrain data adequacy. And this is a good example of how sampling biases can majorly constrain data adequacy. On the other hand, the random method gave us extremely high completeness, suggesting that completeness is likely limited by biased sampling rather than the number of specimens collected. So it's not exactly how much data you have, but where you have it. In addition, we also looked at sampling effort across the United States. And so on this map here, the size of the dot represents samples to species ratio, and the color of the dot represents expected species richness. So a Very small and light dot would mean not very well sampled and not high expected richness, whereas a large dark circle represents an area with high expected diversity and it's well sampled. And so looking at this map, we see that many potential hotspots of richness, like the southwestern United States, have low degrees of completeness and also varying degrees of sampling effort. And we actually know that the southwestern United States does have high species richness, that numerous checklist papers support this. And so we're still seeing low data completeness and lower sampling effort in these areas. And in general, most of the United States shows low sampling effort, especially in some of the southern states. Note that our analyses is just looking at digitized data, and digitization effort is often not equal across collections. And so that adds a whole other element of bias. So conclusions and future directions, we do need to continue digitizing. These specimen records are super important for historical information. They can be used as reference material for trait data and specimen identifications. And once everything's digitized, we can test our constrained versus random methods. So yes, complete digitization is necessary, but it's likely inadequate for filling the data gaps that we have highlighted. So the highest priority should be initiating new strategic surveys to fill these known taxonomic and geographic gaps. I mentioned ongoing and near-term projects. There's an iNaturalist assessment being led by James Hung et al. And this started before our USB's paper started, but it is tangentially related in that it's looking at the importance of community science data and how this data can increase knowledge on many bee species distributions outside of just specimen data. And then 3 other papers, occupancy modeling being led by Melissa Guzman. This paper is using our USB data set as well as additional data sets to run occupancy models for North American bumblebee species. There's another project, the Bee Biodiversity Tropics to Tundra, being led by Angela Bolanos. And that again uses our USB data as well as data from other parts of North America down to parts of South America to run species distribution models. And then there's a global bee data paper, and this is really more of a data informatics paper. And a huge benefit is the R package that's being created that will help clean global bee data. And again, as mentioned, we really hope to use these results to provide projected assemblages for conservation and regional research efforts purposes, like to NatureServe. All right, and with that, I will take any questions. Thank you.